Hello everybody. In this lecture, we are going to cover Green's formula and the jump formula. So let me start with a simple fact. So we consider the so-called Heaviside function, hx equals to 1 if x is positive, 0 if it is negative. Then we can try to compute the derivative of this Heaviside function, and in the sense of distribution, and we are going to obtain a Dirac mass. So let me just verify quickly this fact. So if we consider any test function on the real line and we compute phi prime negative of integral of f phi prime h of x dx, since h takes the value 1 on the interval 0 infinity, 0 elsewhere, we have nothing but this integral. And so the primitive of this function on the point 0 gives phi of 0. Infinity gives the value 0 because function has compact support. So so that we have obtained the desired formula. Okay, so this proves that the delta not Dirac mass at point 0 is the derivative of h in the sense of distribution. So this actually gives a prototype formula for what we want to show. So this is the function Heaviside function, h of x. So it has only one jump of the first, it has a discontinuity of the first kind, meaning that it has a jump on this point 0. And the derivative is a point mass on this point of jump. And so this is the simplest jump formula. So more generally, we can consider those functions which are C1, piecewise C1, and it has some jumps at certain finite many locations. Then we can also obtain a similar formula. And this is the content of theorem 8.2. We consider this one-dimensional jump formula. So we're given f real-valued function, piecewise C1 function defined on R. It has continuities of the first kind on the point A1, A2, AN. These are ordered points on the real line. So then we can compute the derivative of this f in the sense of distribution. So I always use this kind of notation. T sub f means that the distribution associated with this L1 log function. Here the function is clearly L1 log because it's C1 with discontinuity of first kind. So all that makes sense. These two distributions make sense. And what we have is that the distribution f, take derivative of that is equal to distribution associated with f prime, which is only defined on R when we subtract all the points A1, A2, AN. So this quantity is well defined on the open set R with A1, A2, AN removed. And we have additional term which corresponds to the jump term. So the f, this square bracket, f means the jump size of f at the point AI, and delta AI is the Dirac mass on the point AI. So this is indeed this is a generalization of what we had before for Heaviside function. So let's see how to prove this. It's actually not much more difficult than the simple fact. So we prove theorem 8.2. Let's do the proof. So we consider generic test function, and we're going to compute a negative integral of f times phi prime dx. And this we can do we can decompose the integral into a sum because they behave differently on different intervals. So first interval is negative infinity A1. Then we have sum I from 1 to n-1 integral over AI plus 1. So this gives the integral in the integral on the interval a1 to an, and we decompose it, and eventually we have this an to infinity f of x phi prime x dx. All right. So the first term, if we apply, if we just integration by parts, we have the boundary value, which gives actually f of a1 minus. A1 minus means the limit from left of the function f on the point a1, and phi of x. This is because we have a phi of a1 minus is the same as a1 plus, so it doesn't a1. So it doesn't matter. We take plus or minus. It's a continuous function phi. So the other endpoint is just 0 because phi has compact support, and f is a C1 on that interval. Okay, so then we have this integral. Negative becomes plus f prime of x phi of x. So this is integration by parts for the first integral in here, and we can apply the same trick, right? So we do integration by parts for all the sum, all the summand, which are also give rise to the boundary value ai plus 1 with a negative. It's the limit from left. Phi of ai plus 1, again continuity, then minus f of ai plus the right endpoint because we are on this interval, right? The right limit on ai times phi of ai. So this is the boundary value, and then negative becomes plus. We do the integration by parts. ai plus 1, then f prime of x phi of x dx. All right, so it remains to do the same thing for the last integral, and we're done. Right? So last integral, the boundary point is an plus phi of an. Okay, and the other endpoint is 0. Finally, becomes a plus, so an infinity f x prime phi of x dx. Okay, so we're almost done. So now we put all the integral of this type together, and we recover the integral. So this is the first piece. We recover the integral on the whole real line f of x phi of x. On the other hand, if we put all these differences together in the right way, so in such a way that we can take out the common factor phi of ai, and then we compute the difference. So we are going to find that this f the sum. We're going to find exactly what we wanted actually. So we're going to find f of ai plus minus f of ai minus, which is precisely the jump size of f on the point ai, phi of ai. And this, according to our notation for distributions, L1 log functions. So this is nothing but t f prime of phi, and the second term is what we wanted. So it becomes the sum over I from 1 to n, and the jump size, this is our notation, f square bracket f, jump size on a point ai times the direct mass on the point ai applied to phi. And this finished the one-dimensional jump formula. All right. So it is natural to ask the question for higher dimension, and the simplest case in higher dimension would be to consider a function f here. Consider a function f which is the indicator of a smooth open set U included in RD. Okay, D larger than or equal to 2. So in view of this fact about Heaviside function, we expect that this f prime, so here is a typo, I should use a partial derivative because we have more than one variables. So partial derivative of f should be related to a certain measure on the support on this on the boundary of this of the open set. So the boundary of the open set for this in this case is actually just it's just the point 0. So eventually we have a point mass on the point 0. In general, we have this the boundary of this of the open intervals will be these AIs. Okay, same in this general theorem. So in higher dimension, we should really expect to have certain measure on the boundary of this of the open set. So to this end, we actually need the notion of surface measure on hypersurfaces. So this is the goal of this following proposition theorem 8.3. It says the following. So we consider omega an open subset of RD, and F is a C1 omega with the property that its gradient vanishes on the 0 set of the function. Okay, so whenever fx is equal to 0, we have automatically gradient of f of x is not 0. Okay, so the function doesn't vanish on its 0 set. The gradient of the function doesn't vanish on its 0 set. So if this is the case, then we can find a positive distribution that we call delta f. Okay, sometimes it is called the Larrey measure in PD literature, and in probabilistic literature, this kind of thing. The measure supported on the 0 set of stochastic processes is called the local time. So this kind of thing supported on the 0 set of f. The 0 set we're going to denote it by sigma, capital sigma, such that for any h continuous function with compact support in R with integral 1, this function, this is like approximation of identity, right? So this 1 over sigma h of something over sigma is the approximation identity. And so we claim that there exists a measure delta f such that this kind of thing, this kind of approximation of identity of f converges in the sense of distribution to delta f. So we know that 1 over sigma h of something over sigma converges to delta on 0. So that explains why we're using this notation delta of f, because there's an f over there, right? Okay. Moreover, if we have another function g, which is also c1 omega, with the same kind of property that we have in equation 1, meaning that the function g does not vanish. No, sorry. The gradient of g does not vanish on the 0 sets, the 0 set of g, exactly this property for g. Then we have necessarily gradient g times delta g equals to gradient f times delta f. Okay, so we actually need to make sense of this kind of thing, because we have a distribution and we want to multiply distribution by a C-infinity function. We can do it, right? And here we can still do it for the following reason. We are going to show that this guy is a positive distribution. By a previous result, we know that all the positive distributions of 0 order. And the good thing about a finite order distribution is that we can extend its definition to a larger class of functions. So it actually extends to a continuous linear form on the space of continuous functions with compact support, okay? Because the order is 0 in here. So we can extend it to continuous function with compact support. That being said, that explains why we can define this multiplication of a distribution by a continuous function, because f and g are C1, so gradient is a continuous function. This makes sense. The product makes sense. Okay, so there are several things we need to show in this theorem, And we're going to show that in several steps. So the first step, theorem 8.3. Okay, the proof. The first step will be to show that for any A, so we're going to localize the problem actually. So for any A in the support in omega, right, open set, there exists a certain neighborhood of A, it's open subset of omega, such that this mu epsilon converges to delta F. I can call it delta FA, right? So in the sense of distribution, so VA. This is what we want to do. We show this. Actually, we show the convergence locally. We consider only a small neighborhood of any point inside the open set omega. And how to do this? So we are going to distinguish two cases. Okay, so the first case is when f of A is different from 0. So if this is the case, then we can find VA, which is the neighborhood of A, open subset of omega, such that there exists a C, all the points inside the VA, the function takes the value is away from 0. So this is the point. This is away from the 0 for any x in VA. Okay, VA is the neighborhood of A. And also, since the function h is taken to be C continuous with compact support, okay, we know that the support of this 1 over epsilon h of something over epsilon. So this something is the variable of this function. So this support is actually will be contained in, say, negative C over 2, C over 2. So eventually this guy actually will shrink to the origin if epsilon goes to 0. The shrink to the origin is it becomes a smaller and smaller shrink. Shrink to the origin if the support contains the origin, of course. Otherwise, it's just becomes smaller and smaller. In any case, it will be included in this set, C over 2, negative C over 2, C over 2, when for all epsilon small. Okay, so if this is the case, the function takes the value larger than the value of the function range of f, range of VA by the function f will not intersect the support of this function, so the value will be 0. So this is the consequence. This will be constantly 0 for all the epsilon small. So since it is constantly 0, we obviously have that it converges to 0. And since we have this convergence to 0, we can, yes, we have also convergence to 0 in distribution. In the sense of distribution, we apply to a test function. We can show that it also converges to 0 by using a dominating convergence theorem. Okay, so the other case is much more complicated than this. So we have to show that there exists a non-trivial object as the limit. This delta f thing. So the other case is when f of A is equal to 0. So A is in the 0 set of f. For the sake of the proof, let me just write A as A1B included in omega. It's a point in omega. And we know that this function, the gradient of the function f on the 0 point doesn't vanish, right? On the 0 point doesn't vanish. So in particular, we know that one of the gradient, the one of the partial derivatives is not 0. So without loss of generality, we can actually assume that this one of the thing, the first partial derivative is different from 0. Okay, up to a rearrangement of the basis vector in RD, we can always do this. Okay, so now we can from this this condition. So we have a function takes a value 0 on A, and one of the partial derivatives is different from 0. Then we can apply actually the implicit function theorem to find a relation between the first coordinate and the second coordinate, such that f of so let me just give a precise statement. Implicit function theorem. So we can find, first of all, a small neighborhood of A1. We can find a small neighborhood of A1, small neighborhood of B. So these are the neighborhoods of A1 and B respectively, such that there exists a Q which maps from W to I, such that f of x1 y is equal to 0 is equivalent to say that x1 is equal to Q of y for all the x1 y in the product space in the rectangle I times W. Okay, this is implicit function tells us this. So so to have a picture of what we're doing here, so this equation actually defines a surface, right? So we have a function of d variables are in x1 is in R, so I didn't say that. I should have said that. So this is in R. This guy is RD minus 1. So we have a function of d variables. We separate the first from all the others, and so this actually is here 1. Okay, so this equation actually give rise to a surface, right? So in the to give rise to a hypersurface. So if d is equal to 2, this gives rise to a curve. D is equal to 2, they give rise to a surface, okay, a real surface. And higher dimension give rise to a hypersurface. So this actually, the implicit function theorem says that we can actually parameterize this surface as follows. So the first variable is it can be parameterized by the second one, so that this guy defines the same hypersurface that we have in here. Okay, so this theorem is very important. So now we have a explicit, we have an expression of xy in terms of y, such that we are working on the hypersurface or on the level set, 0 set of the function f. Okay, so the point is that now we can have an expression for the function f x1y by using Taylor expansion. Okay, let me just use Taylor, first order Taylor. So f of x1y, we can just write it as q of y plus. Okay, so we do the expansion on the point q of y. And recall that we have already said that this function satisfies if x1 is equal to q of y, then this guy is equal to 0. So this guy actually is equal to 0. And so Taylor expansion, we have the first linear term, just the first linear term, and the integral from 0 to 1. So the partial 1f of, so now we have actually this q of y plus t times x1 minus q of y times dt. Okay, so let's define this quantity. Let's call it, give it a different name. Oops. Let's give it a different name for this integral. So we're going to call it m of x1 y. Okay, so this function is actually it's a continuous function because f is a C1 function. This is a continuous function on, of course, I times w. Okay. Okay. So this we can plug this expression. So we can plug this expression. First of all, this is equal to 0. We can plug this expression into the definition of our mu epsilon, and to try to show that there is a convergence. There's a limit. Right. So this is what we're going to do next. We consider any function phi, test function, and we're going to compute mu epsilon of x phi, and the goal is to show that this guy actually converges, right? So first I use the definition. So it's a double integral on I w, 1 over epsilon h of, here is just definition of the function mu epsilon. So denominator is like this. The numerator is f of x, and f of x we can write by using this expression. It actually can be written as the product of the linear function with mx1y. So this is what we have. Product of this guy with mx1y. Okay, times phi of x1 y dx1 dy. Okay, so this is for the moment we haven't do anything. We just use Taylor expansion to re-express f in terms of product two functions. And so next step we're going to make a variable change. So let's assume, let's do the following variable change. Z equals to x1 minus q of y divided by epsilon. Okay, so this is our variable change, and we're going to have that this okay, so we can write w, and we are going to extend it to the whole, we are going to extend this I to the whole real line. We can do that because we have some function with a compact support, right? So outside of it's just 0. Okay, so h, after doing the change of variable, this becomes, here we have this guy equals to z, so z times this quantity, but we also have x1 inside m function, so we need to replace it by the function of z. Anyway, we are going to have z times m of, so we replace x1 by z epsilon plus q of y. This is the first variable, second variable just y. And time, okay, finish the parenthesis. And now phi of x1 is z epsilon plus q of y. Then dz dy. Okay, very good. So if we consider only the inner integral, so let's just consider inner integral in here. Just this guy, okay? So the inner integral, the gray colored integral, actually converges to the following quantity. Let's see, so when epsilon goes to 0, this guy actually disappears, and it remains only phi of qy y for this person. And for the other piece, we have if goes to 0, this also disappear. We remains only z times m of qy. So we do have a conversion, pointwise conversions. And if we make use of the fact that phi is also h are functions with compact support, we can make use of dominant convergence to justify that the inner integral actually converges to this much simpler quantity. So h, so in R, so h of m q of y times there's a z. Sorry. Okay, so this is the first piece. dz can separate it because this does not depend on z anymore. Inner integral converges to this quantity, and we see automatically by making a variable change that this guy is 1 over the absolute value of this m function times the integral of h, which is equal to 1. So this guy actually equals to a quantity f phi of q of y divided by the absolute value of m. Okay, and let me recall what is m. M is this function over here. It's integral of this partial 1 f. And when x1 is taken to be q of y, this guy disappears. And then we have just d1f of qy. That's it. And this is what we have. Wait a minute. So here y doesn't change. I forgot to put a little y for the second variable in here. It doesn't matter. Okay. F is a function of d. F is a function of d variables, and this is only real value. I forgot to put a y over there. It doesn't change anything, but there's a y. So the point is that this guy, when we take x1 equals to q of y, this disappear. We only have d1f of qy y. So, in other words, we have something that looks nice, right? So we have something that is related to the function f and function q. Okay, so this is the inner integral, and by using again the same kind of argument, we have the pointwise convergence for the inner integral. Then we can make use of dominated convergence to show that actually the whole integral with respect to y on w also converges. So by dominated convergence, we can show that as epsilon goes to 0, this guy, so mu epsilon, x of phi of x dx, this actually converges to an integral on dw of phi of q of y divided by partial 1, so d1f, q of y dy. Very good. So now we can actually write this numerator, this denominator, this d1f, more explicitly. So this kind of depends on the choice of our coordinate, because we say that the function has non-zero partial derivative. This is the general assumption that we have for the function f, and then we assume without loss of generality that the first coordinate, okay, so the partial derivative with respect to the first coordinate is non-zero, and we would like to get rid of this this dependence on this choice. So we would like to have an expression for the limit in terms of only the gradient of f and also possibly the function q. Function q is the implicit function we found in the implicit function there. Okay, so these are more universal objects. So let's see how we can do this. So actually, it's simple because we can actually compute the gradient for this for this equation. We compute the gradient of this equation, f of q of y, y equals to 0. So, so if we take the grad with respect to f of this left-hand side, we should have 0, right, according to the equation. But by using chain rule, this guy is nothing but partial derivative with respect to the first variable of f, q of y, y gradient y, q of y, because q is just a function of the y variable. You can forget about this y in here. And plus gradient y f, q of y, y. And we know that this is equal to 0 according to this equation. So we have 0. Okay, so put things together, we can actually have that gradient of f apply to any point. So here, q of y, y. So this can be written as, this is by definition, it is gradient with respect to the first variable of f on this point, and the gradient with respect to the y variable of f. And that one, according to previous equation, this guy can be written as negative sign of d1f times gradient of q. This is what we have, times gradient q. Okay, so obviously we can pull out this real valued quantity times 1 on the first component of this column vector, negative sign of gradient q on the second. Okay, so all this dot denotes QYY, the point QYY, which is on the surface, on the hypersurface. Okay, so from here we can now, we have an expression. So gradient f, so of course always on the point on the surface, is equal to square root of 1 plus delta q. Now this is gradient q square times the absolute value of d1f. Okay. In other words, 1 over d1f can be written as square root of 1 plus gradient q Euclidean norm squared divided by the Euclidean norm of gradient f. Let me just recap. So what we have is the following. So we established the convergence mu epsilon x phi of x dx converge to this w phi of q of y y. Okay, so this is what we have in here, this convergence, times 1 over d1f, which can be re-expressed as 1 plus gradient q of y, Euclidean norm squared divided by gradient of f, Euclidean norm dy. All right, so this is our limit, and we're going to call this guy delta f a because it is local, phi. So this clearly defines a positive distribution. Whenever phi is positive, this quantity will be positive. Okay, so this is as needed. Delta f, delta, it follows. So we find the limit also, this is a positive distribution. On VA. So this is our local solution, our local convergence of the family mu epsilon on any open set inside omega. All right. So let's do the following step, which is to glue things together. So this we're going to have a global convergence now. So step 2, what do we do? We're going to do the following decomposition. We're going to call omega this union of all the VA if A is a 0 point. Otherwise, we have another open set, which is the set on which x is not 0. Okay, 0 set is a closed set. This way, this guy's open set. So we have an open cover of the omega. Each one of them we can show convergence. So this is typically a situation where we can make use of the partition of unity to prove things. So all the k for any k compact subset of omega, and we can find a covering. We can find a, of course, find a covering, also a partition of unity. So we call this family chi A for A in some certain R, which depends on K. This is a finite set. So we have make use of this kind of argument before. The support of each of these guys will be included in VA as needed in here. So we only need finitely many of them to cover this function K. And also we have this chi of A is equal to 1 on the support. Okay. So for any phi in test function with supporting K, so we have that epsilon phi. We can write it actually as some A in R. R is a finite set. So mu epsilon applied to now chi A times phi. So this guy is supported in VA is a test function supported in VA. So we have the convergence for this kind of quantity. We have already shown that. So eventually we have the convergence that this is A in R finite sum, so delta F on A phi chi A. Okay, we can pull it in and we have a finite number. This is a clearly this is a finite number because this guy, we have shown that this is a distribution. So the sequence applied to test function converges, and previous result says that it converges to a certain distribution. Okay. So mu epsilon converges in the sense of distribution. All right. So now we can make use of this this compatibility condition of the gluing principle that we have shown before. So there exists only one distribution which extends everything, which we obtain when we glue together all the distribution on all the sets in the open cover of omega. Okay, so by the gluing principle, it has to be the case that any phi test function we have delta F applied to phi. This is equals to, now this is actually our d minus 1 phi of q y y square root of 1 plus gradient q y Euclidean norm squared divided by gradient of f q of y y Euclidean norm dy. Okay, so this guy, when we restrict it to a VA any of the set in the covering, it coincide with what we have in the limit, with this what we call delta FA. Okay, and so by the uniqueness in the gluing principle, this has to be the limit in the whole set omega. Okay, this is the step where we show we have a convergence in the whole set omega. So it remains to do the final claim. The final claim says this: if we have another C1 function with the same zero set is also sigma, and the property that its gradient does not vanish on the zero set, then this product gradient G Euclidean norm times delta G is equal to Euclidean norm of gradient F times delta F. The final step is to show this claim. As already said, there's no problem in defining such a product because this is a positive distribution, so zero order distribution. Multiplication by a continuous function is not a problem. So what we need to show is just that we have another function, we want to show the product, they're equal. So the first thing we can do is the following. So we can actually compute this for any test function. We can compute gradient F delta of F. There's no problem in defining such a thing. As I said, it's F applied to gradient F phi, right? So if we do this calculation with our formula given before in here, let's give it a name. Let's call it the star function. Given in star, then this gradient F will actually cancel with this gradient F in the denominator. We end up having this integral of phi of q of y times 1 plus gradient of q y squared Euclidean norm dy. And this is what we have. And we realize this right-hand side actually does not depend on f at all. It depends only on this function q, and q is intrinsically related to the hypersurface, which is the zero set of the function f. If we have another function g, so let g be C1 omega satisfying the condition 1 that we have in here. It does not vanish on the zero sets, and x g of x is 0, the zero set, coincide with that of f. Then necessarily g of x q of y is equal to 0, because this is a 0. This point is a 0 of the function f. So according to this, it is also 0 of the function g. Okay. So if this is true, then we can make use of the same trick as before. We can take the gradient of this guy. We can take the gradient of this guy, and we're going to be able to find, and by the same trick, we can find gradient of g is equal to square root of 1 plus gradient of q squared d1g. Okay. So the point is that we have exactly the same thing for this. We have exactly the same thing for this gradient of g. So now it's just we have instead of putting in here, instead of putting the gradient of f in here, we put a gradient of g. Okay, and that's the only difference. So by multiplying the same quantity by the gradient of g, it will cancel this gradient g on this position, so that we have exactly the same. So repeating the same argument, leading to the star equation, we have the gradient of G delta G applied to phi equals to the gradient F Euclidean norm delta G delta F applied to phi, and both equals to this quantity. And this finished the proof. Okay, so this is a very important result. It actually says that we can define a measure. This measure will not depend on the precise function that we choose, the C1 function we choose. It depends only on Q. So the point is that it depends only on Q function that we find in the implicit function theorem. And this Q is intrinsic with respect to the hypersurface, that is the zero set of this function f. Okay, but if we choose another function, any function, C1 function with the same property, we end up having the same thing, right? So in the following, we call this sigma the product of the two things sigma, and this will be called the surface measure associated with the hypersurface sigma. Okay, and there's no ambiguity in defining such a thing because it does not depend on the choice of this function. It depends only on the set sigma. All right, so just two more facts before we move on. We have seen from the proof that for any test function in here, in the test function, continuous function with compact supporting omega, we have that the convergence of mu epsilon applied to phi to the, so this guy is actually, if we look at the formula for sigma, so sigma divided by delta f, which is which doesn't vanish on the support of the measure, which is sigma. Okay, so this makes sense. So this guy gives back to this delta f, which is a measure supported. This is a local time or Lagrange measure supported on the zero set of f. This delta f. Okay, so this is what we showed. We showed as a mu epsilon convergence to delta f. So this is what we have. On the other hand, if we want to evaluate the integral of a function with respect to this surface measure sigma, so what do we have? We actually have that the surface measure, we can actually write it in terms of this function q, and the integral with respect to a Lebesgue integral on the d-1 dimensional space. So this is what we have. If we compute the rectangle on this integral on the rectangle I times w satisfying this property. Okay, so this is actually a neighbor. Okay, this is nothing but a bunch of points on the hypersurface, right? A subset of the hypersurface. Then we can just integrate the second variable with respect to the big measure on a d-1 dimensional space by using the q function that we have. So this is universal with corresponding to the set sigma. Okay, so we need a few more definitions in order to state our formula, our distributional version of Green's formula. It's about some geometric definitions about a surface, the smoothness of a surface. So we are going to consider omega this time, also always an open subset of RD, and this closed C1 hypersurface of omega is a closed subset of omega denoted by sigma, such that for all the point on this closed set sigma, we can find an open neighborhood and a C1 function on the neighborhood V, such that the function equals to 0 on the restriction of the surface on the in the open set V, and the gradient F doesn't vanish on this on the intersection of sigma and V. So let me draw a small picture of to tell you what is going on here. Let's consider omega very big, and this sigma is just in 2 dimensions is just a curve, right? 2 dimensions is just a curve. Omega whatever is just R2, say, and this is my sigma, a curve, and I call it C1 hypersurface. I call it C1 hypersurface. If for any point, okay, on my closed set sigma, I can find a small neighborhood. This is A, and this will be called a V of A, the small neighborhood of A. And the function fa defined on V, which is C1, so this is an open set, V, such that F vanish on the intersection of omega of sigma with VA. So in other words, it vanishes on this curve in here, and the gradient on the point on the point doesn't vanish. So we have a function implicitly. We cannot see it in the picture, but the function vanishes in here, and the gradient doesn't vanish on the same set. Okay, so if this is the case, then we call it sigma C1. The sigma will be called C1. This curve in here with C1. In higher dimension, if d is equal to 3, we are going to have a surface. Then it means that whenever we consider a point on the surface and we can find a boundary, say a ball centered at this point with some radius r, such that we can find also a function f inside of ball, C1 in the ball, with the property that it vanishes on this intersection of the ball with the surface, and its gradient doesn't vanish. Okay, so if we use our already proved the theorem 8.3 together with the gluing principle, we can actually show without any difficulty the following proposition. It says that if you have a closed C1 hypersurface of omega, we call it a sigma, then there exists a unique positive measure sigma supported on this small sigma supported on capital sigma, such that for any open subset of omega and any C1 function in the open set V, with the property that the function does not vanish, with the property that the function vanishes on the intersection of sigma with the open set V. Also, its gradient doesn't vanish. It's exactly what we have in the definition. Then we necessarily have that the sigma is the product of the Euclidean norm of gradient f times delta f. These things we can compute, right? These things we can define with the help of our theorem. Okay, so this measure will be called a surface measure on the closed C1, this closed C1 hypersurface sigma. Okay. So the point of this definition and also this proposition is to kind of generalize what we have in the theorem. In the theorem, we have said that we are given ahead of hand a C1 function, then we can construct a surface measure on the zero set of this function, satisfying certain property. Okay, and now we say that in a more general setup, we can also construct a surface measure on a surface which is locally in this situation. So locally, in the sense that for any small a, for any a on the hypersurface, we can find an open neighborhood and the function such that everything in here is true. Okay, so long as we have a surface of this kind, then we can also define with exactly the same proof by using gluing principle. We can also define a surface measure on this kind of surface, which is more general than this, than just the zero set of a particular C1 function. So we can have a slightly more general definition of the hypersurface and the surface measure on the hypersurface. Okay, so now we can define another thing. So for the moment, we have defined a measure on the hypersurface. So now we define what is so-called open subset of class C1. So what is a class? What do we call a class C1? Is those open subset of omega such that the boundary is a closed C1 hypersurface. Okay, the boundary of this is what we have already defined. This closed C1 hypersurface. For the first requirement is that the boundary is a C1 hypersurface, and the second requirement is that locally U looks like U is on one side of sigma. Let me just draw one picture before getting into the mathematical definition of this on one side of boundary of U. So it actually means that, so if you look at really very closely to a certain point on the boundary, we can find a small neighborhood such that our U, so this is our U, is only on one side of the boundary of U. Okay, so this is the case. For instance, this is a yes. On the other hand, if we consider another situation where we have, for instance, the set will be the subtract, so x1 is equal to 0. Okay, so in 2 dimensions, for instance, we just have this. Okay? X1 is equal to 0. So the set is given by this open set, the R2 removed with this vertical line removed. And if we look at the boundary of this open set, no matter how small we draw this, we draw a ball, we don't have the property that U is on one side of the boundary, right? We actually have both sides. So this is not an open set of class C1, and this one is. The first case is. Okay, so mathematically actually means that for any A on the boundary, we can find an open neighborhood of A denoted by V, and we can find a function f C1V, which is C1V, such that f, this function, takes the value. Let me draw another picture here. So this is our omega. Okay, this is our U, and we have a boundary of U, and we consider a point on the boundary, and we can find a V of A. This is V of A, and the function f such that it takes the value 0 on the intersection of the boundary with the neighborhood VA, 0 in here, and positive value, takes a positive value inside in the intersection of V and V and U. Okay, this is the case. Okay, so, and also this function does not vanish on the zero set, on its zero set. Okay, zero set in this case is nothing but the intersection of the boundary with the neighborhood V in here. So this is positive in here, and the gradient doesn't vanish, so necessarily on the other side we are going to have negative values on the point A. On the one side we have positive values, and also know that the gradient doesn't vanish, so it's a monotone function along this normal direction, so that the other side will be taken will be taking negative value. Okay, and we're going to call the gradient of f. So this direction is actually determined by gradient of f. Okay, and if we divide it by the Euclidean norm of gradient f on A, then we have a unit vector. And this vector will be called the inward. This vector will be called inward unit normal vector to U on the point A. A is a point on the boundary of U. And this here is our definition. And the outward unit normal vector will be just the negative sign of the inward unit normal vector, defined as such. Okay, so now we are finally ready to state our distributional version of Green's formula. Let's say, let's see what it says. It says that if you have a U which is open subset of omega of class C1, this of class C1, then for any j, the partial derivative with respect to the j variable of the indicator function of U is equal to the j's component of the inward unit normal vector times the surface measure on the boundary of U. Okay, so this is the unit, the inward unit normal vector, and on the other hand, sigma is the surface measure of the boundary of U. So let's give a proof of this result. So our idea is to use a approximation sequence of the indicator function. And since we have continuity for the derivative on the space of distributions, once we have the convergence towards the indicator of U, take the derivative for the approximating sequence, it will converge to the right hand side, to the partial derivative of indicator, and we're going to show that this guy is equal to the right hand side. Okay, so this is our strategy. So to this end, let's introduce a function. So theorem 8.8, proof. We introduce a chi function, which is a C1 on the real line, such that chi of t is equal to 0 if t is negative or 0. It's equal to 1 if t is positive, larger than or equal to 1. So we don't care its value in between. So we are going to have that for any A on the boundary of U. Okay, so we're going to show this again locally. For any boundary point, we consider a neighborhood of A called V, and a function C1V in the definition of a open set of class C1. Okay? Open set of class C1, we can find such a, for any point on the boundary, we can find the neighborhood and the functional in the C1 function in the neighborhood, so that it vanishes on the boundary and its gradient doesn't vanish on the boundary. Then U of the gradient, the indicator of U will be the pointwise limit of this function, chi of f of x divided by epsilon, as epsilon goes to 0. Now this is true for all the x in V. This is locally true. So there are only two cases. The left-hand side takes only 0, 1 value. if x belongs to u, then f of x, according to this definition according to the definition of f in here, we know that takes the positive value inside the u, the open set u. In other words, so f of x, if x belongs to u, actually is a positive. Divided by epsilon, as epsilon goes to 0, this guy actually goes to infinity. So in any case, when epsilon is sufficiently small, this guy becomes larger than 1. So the value gives the limit value will be 1 according to the definition of chi. On the other hand, if x does not belong to u, then we know, as we have just said in the picture, so we know that at least when epsilon gets very, very small, we have the value of the function f on the point A is equal to 0, and it is completely positive inside the open set u. On the opposite side, it will take the negative value, right? And so that as epsilon goes to 0, this guy actually goes to eventually becomes 0 according to the definition of chi again. In any case, we have this point-wise convergence, and also by using the uniform boundedness of the function chi, we can show by using dominated convergence theorem that this guy converges in terms of distribution, also in distribution. So also we have convergence in d prime of v. Okay, so this is the first observation. Since we have this convergence, then by using the limit will be, okay, let me just rewrite. By using the continuity of the derivative on the space of distribution, we have this value is equal to the gradient of j f of x epsilon. So this limit is in the sense of distribution. Okay? If we take a partial derivative, we also have a convergence. And convergence is the partial derivative of this function we have, the limit function we have. So it remains to consider this partial derivative. Now it is a real function, and it is so now it is actually a composition of a C1 function with a C1 function. So it is really it is a C1 function. So this makes sense, and we can actually have a convergence. So to be more precise, this guy we use here. We use chain rule to have that it becomes j of f of x chi prime of f of x over epsilon. There's a 1 over epsilon that I forgot here. So we realize that here we can actually identify something that we know. So this guy together with this 1 over epsilon. We put them together, we realize that this is a specific situation. Since h defined as 1 over epsilon chi prime of x, let's call it y, over epsilon. So this guy is actually continuous with compact support in R. Continuous because chi is C1 with compact support because of the definition of chi. It is supported actually in the interval 0, 1. So this probably is true. Also, the integral of the function of this function actually is equal to 1. Again, by the property that we have on the function chi, we can actually have a convergence. So this guy will converge to, on the right side, this guy will converge to, as epsilon goes to 0, to delta f. Okay, this is what we show in the very first result. And times gradient j, no, this partial derivative with respect to j variable f of x in the sense of distribution. Okay, and this, we're almost there. Now, just we rewrite it. We're going to write it as delta j f divided by gradient of f Euclidean norm times gradient of f Euclidean norm delta f. We recognize that this is nothing but a surface measure. And this guy is nothing but the j's component of the inward unit normal vector field. And this is the result. Okay, this is almost the result. This shows that we have the convergence, we have this identity in the set. So indeed, this guy is equal to nj times sigma in V. Then by using, again, so the same kind of trick that we did before, by the gluing principle, we can show the same thing, which holds in the whole. So also, this is also true. In omega by gluing principle, which finishes the proof. Okay, now that we have this this new formula, this is distributional formula, green formula, we can make use of it to recover a bunch of results that we have known already from multivariate calculus, right? So now we have a quite rigorous proof of those facts. First thing is Gauss-Green formula. And the Gauss-Green formula is really just the same thing as a green formula when they applied to a test function. So this is a distributional identity. This guy applied to a test function C1, C1 naught, right? So this guy is of, so since the integer of u is of 0 order, this guy is actually of first order, and it can be extended to test function C1 test function with compact support. So this is where we have. This guy applied to test function, left hand side, equals to this guy applies to test function, right? So since this is the derivative of u, we have, let me just write it out. It's a simple exercise. So j indicator of u applied to this is equal to the negative sign of integral of u partial j phi x dx. Okay, this is the left hand side, and we also know that the right hand side it defines the product. So again, phi of x times n interior, this inward unit normal vector, j's component of x, sigma dx. This is what we have, and we also know that it's actually supported on the boundary. So it's actually the boundary of u, right? And so this is exactly what we have as a Green's formula. Just we put this negative sign together with this inward normal vector, which becomes outward normal vector that we have in the formula in here. Right? Exactly the same thing, just applied to the test function. On the other hand, if we put everything together in here, so recall that the divergence of a function, of a vector value function, here we assume that we have chi is a C1 function omega, which maps to so D maps to RD. So d-variate. Then the divergence of phi is given by j from 1 to d partial j of the j's component of the vector field phi. Okay, so really the divergence formula is just when we put everything together, we put all the components together, we can have this. The right hand side we have the inner product for the odd per unit vector field with the vector field phi. Okay, so finally we are ready to state a multivariate version of the jump formula. The proof is quite light because we have done all the hard work before. So let me give a final proof. Theorem 8.10. Now, let me state the theorem first. Omega is an open set with C1 boundary. Okay, so this means that omega is of class C1. And the boundary will be denoted by capital sigma as 0. And f is, consider a function f which is C1 everywhere except on the boundary of omega. Okay, so this is the meaning of C1 RD with sigma removed, such that this function extends to slightly larger than, let me draw a picture here. So the function is a C1 on the open set, like this, and it extends to, so restriction of the function inside the open set omega can be extended to slightly larger than the closure of the set. If this is the case, then there's no singularity actually no singularity in the sense that on the boundary, the value of function does not explode. Actually, it's locally the function f is locally bounded around the boundary of this function, and it is actually continuous function everywhere else, so that this function is globally, it is actually locally bounded. So this two definition is actually the counterpart of discontinuity of the first kind in higher dimension, right? So the function behaves quite nicely around this boundary of the open set omega. Okay, so as I said, we have, if this is true, then we argue that the function is locally bounded. In particular, it will be locally integrable. Okay, so it defines a distribution, and we can compute its partial derivative. And this partial derivative will be obtained by first the partial derivative of the smooth part, which is defined only on RD with sigma removed, plus the jump size of the function f. We're going to see this jump size defined as such. It is related to the function value of the function. So this is the point A on the boundary point A. So if we approximate A from the vector normal direction, from this direction, we have one value from that direction. From the opposite direction, we have another value, and the function has a jump on this point, and this characterizes the jump size, this quantity. So we have this jump size times the inward unit normal vector field on its j's component times the surface measure on the boundary of this of the open set omega. So this looks very much likely, it really resembles this formula in one dimension, right? We have jump size times direct mass. Now we replace it by a surface measure. Okay, anyway, let's give the proof. It's not hard, as I said. So proof of the final result. So we consider any phi C1 with a compass supporting RD, and we compute negative integral on omega of the function f dj phi. So this is actually the dj of the distribution associated with f applied to the test function phi, right? This is according to the definition of the derivative of a distribution. And it is actually, we can use the Leibniz rule. It can be written as omega and dj of the product of phi plus omega, then djf times phi. Okay, here's so far so good. And now we can make use of the Green formula, the Green's formula for this quantity, and it can be written as an integral on the boundary, and with interior or this inward normal vector field, J's component of that unit normal vector field, and times f, and I'm going to use f minus to denote the value when we approximate a point from inside of omega, of course, then times phi of x. This is Green's formula that we have, and we are going to integrate the surface measure sigma, and the other piece we don't change, just as it is. On the other hand, if we compute RD with omega removed, the complement of that also with the boundary, it doesn't matter, so the big measure does not charge any surface. So f djf. So this guy, if we apply the same trick, we're going to have integral on the surface of this time. Recall that this guy actually here, we have applied the Green's formula, so where we use the outward normal unit normal vector field. Since we have negative sign, this guy actually becomes an inward unit normal vector field. Okay. On the other hand, the direction, the outward direction for this side and for this side is that they are exactly opposite to each other. Okay, so I think this is pretty clear. This is omega. The invert means this for omega, but invert means that for RD subtract omega bar. They are opposite. They are opposite to each other, and for this reason, we actually have that as invert. We can also have invert in here, J's component, invert unit normal vector field. Then the approximation, the value of the function, approximation of value of the function from inside this open set, which gives the value f plus, which is different from f minus, 5x, sigma dx. On the other hand, we have the same thing, but now RD subtract omega djf phi. So putting things together, summing up, we have that. So here we put this guy with this guy. We have that the integral of djf times phi, which means that, okay, let me just do the left hand side first. Left hand side, actually, we have the integral on the whole RD f dj phi, and that is, by the definition, dj distribution with we are associated with the function f applied to phi. Definition of the derivative. On the right hand side, put this guy with this guy together, we obtain t associated with djf, which is only well defined on RD with the boundary removed phi. So this is our first piece, and we put these two integrals together. We're going to have this guy minus this guy, which is opposite of what we have in the theorem. Okay, the opposite, because we actually have this plus f plus minus f minus. But if we change the inward unit normal vector to outward normal vector, as we have in here, we have plus the integral boundary of dj outward unit normal vector. This is what we have. And then we have f plus minus f minus. And this is nothing but, according to our definition, of square bracket f on the point x, the jump size of f on the point x times f of x sigma dx. And this is nothing but, okay, this is not definition, this is what do we have? Nj outward unit normal vector field times the jump size sigma applied to phi. So eventually we do have the formula as needed. Okay, so this proves the multi-dimensional jump formula, and I just recognize that there is a typo here. This should be an outward unit normal vector field. I'm gonna change it to the final version of the notes. Okay, so this finished this lecture. These two formulas, Green's formula and jump formulas, are very useful and practical in the study of PDEs. So I recommend everybody to understand these two formulas and try a few exercises in the after class. Okay, so I will let's just stop it here, and I will see you in another video.